This is the case of the bar magnet or the magnetic needle. It has got a north pole and a south pole. Though monopoles are not found in nature, but still we can express this like a pole strength. Say m is the small m is the magnetic pole strength, and so this is the length. Roughly we take this 84% of the actual length, but suppose this L, so approximately we can write m into L is capital M. That is this is the magnetic dipole moment. This is the magnetic dipole moment of the bar magnet or the magnetic needle, right? It is, see, you can compare with the electric dipole moment. So you have got two charges plus q and minus q separated by length L. So the electric dipole moment was P is equal to q into L. Similarly, with that similar model, we can think of a magnetic dipole moment as the magnetic pole strength multiplied by length. So the length, it happens to be 0.84 times the geometric length. However, we take this length is equal to L only. Now, we can also compare the magnetic field here with the electric field due to dipole. You know, this position is the end on position or the end side position, and this position on the perpendicular bisector is known as the broadside position. So here also we can calculate the magnetic field. Here this way the magnetic field is mu 0 by 4 pi 2m by r cube, provided obviously all these formulas are valid, provided this distance r is much greater than the magnetic length L. So this is also, this is mu 0 by 4 pi m by r cube. For the electric dipole, you can remember the formulas. For electric dipole, what was the formula? There it is. This was the electric dipole. So there it is, 1 by 4 pi epsilon naught 2p by r cube at a distance r at the end side position, and here at the broadside position it was here, it was 1 by 4 pi epsilon naught p by r cube. Similarly, we can find out torque on a bar magnet or a magnetic needle. So if this is the magnetic needle or a bar magnet, north pole and south pole, and this is the magnetic field at that region, this is angle theta. So there also exists a torque. See, this is the, so from south pole to north pole, this is the direction of the magnetic moment vector. So the torque happens to be in this sense. In this figure it is in the anti-clockwise sense. This torque is equal to mb sin theta. We can compare and write mb sin theta. Okay, and also potential energy of the needle, potential energy of the bar magnet. Similarly, we can write U is equal to minus m dot b. This we have compared with the potential energy of the dipole as minus p dot e. Okay, torque is mb sin theta, so the vector expression for torque is equal to m cross b. So that means the magnetic needle is more stable at this configuration, right? This is south, this is north, this is the stable equilibrium, most stable condition. That means if you let a magnetic needle be free, then it will ultimately settle down in this direction, north pole to south pole, along the direction of the magnetic field at that location. That is it. This is briefly we have discussed about the bar magnet or the magnetic needle. Okay, and again that one, you know, it's similar to find magnetic field at a general location. which is neither inside nor broadside, that also can be done using the following way: south pole, north pole, this is the magnetic moment vector. So at an angle theta r, you have to find here magnetic field B. So again we this is the magnetic moment vector from south pole to north pole. So you can split it up, this magnetic moment, into two, m cos theta and this is m sin theta. So it's like having two magnets. Due to this m sin theta, this is the broadside position. So that is, field is mu naught by 4 pi m sin theta by r cube, and due to this m cos theta dipole, it is the inside position. So mu naught by 4 pi 2m cos theta by r cube. So this will be their resultant field in this direction. Okay. So what we have noticed actually, and all of us have noticed, that if there is a magnetic needle, say if there is a magnetic needle which is suspended from ceiling by a rope which is exactly at its center of gravity, I mean, we don't want any torque due to the weight, that is why suspend it at its center of gravity through this needle. So it will point at a certain direction. Yes. I mean, if you disturb it, then again it will rotate, do some here and there and oscillate, and ultimately settle down at this place. Now you can think that, okay, is this special for this needle? This needle wants to settle down here. Not really. If you bring one more needle, that will also point in this direction. If you bring one more needle, that will also be parallel, all heading towards a particular direction. So there is something in this direction. That something is the magnetic field of the earth. Earth has its own magnetic field. Okay. So this B is magnetic field of earth. Magnetic field of earth. Generally we call it north pole points towards north. That is north pole of the magnetic needle points towards north. I mean, see, don't confuse this thing that many people confuse. This is north pole of magnet. This is the magnetic north of the earth. It's not north of any magnet. It is the north direction as defined, magnetic north of the earth. Okay. So here, as we see that at this location, at this geographical location, this is the value of magnetic field of earth. So you can split it up into these two. This is BH and this is BV. So BH is horizontal component of Earth's magnetic field, and BV is vertical component of Earth's magnetic field, and this angle is known as the angle of dip. Angle of dip at that place. All things are at that place only. All things are this fixed for a particular geographical location. If you move from here to Japan, so this BH, BV and delta all will change. So BH, BV and delta is the angle of dip, and see, all the vertical planes also will be parallel. So this needle chooses its own vertical plane. So that is the vertical plane in which the magnetic needle stays, rather, is known as the magnetic meridian plane. Magnetic meridian plane at that location. This is very important, extremely important thing, magnetic meridian plane at that location. Now we'll judge what is the magnetic meridian plane. It's a certain vertical plane, right? Magnetic meridian plane is a certain vertical plane at a location. Now if this is the earth, now you have the geographic north pole and the geographic south pole. That is, this is the north pole and the south pole. This is geographic. This is also geographic. Now just beside it, slightly tilted, say around about 11 to 12 degrees, like that, there is this north pole and south pole. This is the magnetic north pole and this is the magnetic south pole. And now I will draw the meridian lines. I will draw this with here. Red one for the magnetic and blue one for the geographic. Now you know these are which lines? These are longitude lines, right? Magnetic longitude lines. Magnetic longitude lines, or we call it magnetic meridian lines. Magnetic meridian lines. And similar meridian lines you have in the geographic one. These all lines, right? Maybe a bit clumsy this diagram, but I can't help. So many things in this small place. Okay, so these are geographic meridian lines. Meridian lines are actually great circles. They join the north pole and the south pole, right? Meridian lines are great circles. Great circle means circles of maximum diameter. So these are meridian lines. Okay, now suppose a person is standing on earth at a certain location. This is ground, right? Horizontal, and we draw this at a certain location. This is the magnetic meridian. This red one was for magnetic, right? Magnetic meridian line, and say this one, say this one, like this. This is a geographic meridian line. Geographic meridian line. Now the meridian plane. What is the meridian plane? It is a vertical plane containing the meridian line. It is a vertical plane containing the meridian line. So we will draw the magnetic meridian plane. This is the magnetic meridian plane. I mean this vertical plane. This one. This is the magnetic meridian plane. and the magnet chooses to stay in this plane, and this is the geographic meridian plane. Let's say this one, this vertical plane. Geographic meridian plane. Okay, this handwriting is not good. Okay, just understand this. This is a geographic meridian plane, and the angle between these two planes at a certain point is known as the angle of declination. This angle theta is the angle of declination at a place, that is angle between magnetic and geographic meridian lines at a certain place. However, the main thing is that the magnetic needle chooses to stay in this plane, magnetic meridian plane, right, when it is suspended from a point on the ceiling, provided it is suspended at the center of gravity, because the torque due to weight will not act. That means the magnetic field of the earth, this vector, that means magnetic field of the earth vector lies in the magnetic meridian plane. This B is magnetic field of earth. It lies in magnetic meridian plane. Now, we will not go into the root cause of what causes the magnetic field of the earth, but we can make a simplified model that say this is the magnetic north and the magnetic south of the earth, and the magnetic north and south pole, and the magnetic needles behave as if this is the magnetic equator. Magnetic needles behave as if there were a bar magnet, small bar magnet at the center of the earth. The having south pole this way and north pole this way. Remember, this is the magnetic north pole. This is the south pole of the magnet inside earth. There is no magnet inside earth, but it is the lines of magnetic force outside the earth are such that if there would have been a magnet at the center of the earth, the lines would replicate those lines exactly or closely. So due to this, these are the magnetic field lines. So that is what, see, this is a magnetic field line, and that is why these magnetic field lines, you can see this is the magnetic meridian lines. That is why this B is parallel to magnetic meridian lines. Okay, so we have learned about this. So the magnetic field of the earth, this magnetic field of the earth lies in the magnetic meridian plane. So it lies in the vertical plane. This vertical plane is the magnetic meridian plane. and this B has two components, BH, BV. This is the angle of dip at that place, and if you have the geographic meridian plane at this location, it may be like this one, right? Geographic meridian plane. Then the angle between these two planes at a certain location is this is the angle of declination. So delta is dip, theta is declination, and BH is horizontal component of Earth's magnetic field. So these three are components of, or the elements of Earth's magnetic field. These three, delta, theta and BH. So elements of Earth's magnetic field. So again I'll tell you, a magnetic needle will choose to stay in this vertical plane, which is the magnetic meridian plane. It doesn't have a freedom of choice, it has to remain in the magnetic meridian plane. Okay. Now there is a concept known as a dip circle. What is a dip circle? I will tell you. There magnet is fixed to remain in a vertical plane. Dip circle, it measures dip actually. Dip circle where a magnet is forced to remain in a vertical dial. A vertical dial, that is a dial in vertical plane. Now I'll show you that. Simple as that. This is a vertical plane. A very simplified thing I'm saying. That's a table, and on the tabletop, so there is a needle. A needle is there. There are graduations here, and this is the needle. Magnetic needle. Right now it is pointing there, north south. A very simplified model. It's not like these actually. There are certain more complications, but to know the concept, this is good enough. So this is the dip circle. This dial, this whole thing is known as the dip circle. That is a magnetic dial in the vertical plane. Magnetic dial in horizontal plane we will explain later. Okay. Now at a certain location, this is a very important diagram. This is ground. Okay. And at this location, this is the magnetic meridian line. This line, magnetic meridian line, and you know very well that this plane will be the magnetic meridian plane. So there is no need to write, I have explained it before. And so this is one more vertical plane, just not the geographic meridian, but say another vertical plane, this one. And there can be infinite number of vertical planes. So suppose this angle is say phi. So this is a vertical plane. This one, this brown one, is a vertical plane. At angle phi with magnetic meridian plane. Okay, now we have brought in two deep circles. Now after, as this diagram is clear, I'll draw a slightly bigger diagram that will help me. Yeah, so this is the magnetic meridian plane, and this one is the other vertical plane, right? And this angle happens to be phi. Okay, now we have a deep circle here. We have a deep circle here in this plane, so the magnet will point like this. The deep circle in the magnetic meridian plane, magnet will point with north south like this. This is the angle of dip. See, in this magnetic meridian plane, this is the horizontal component BH, and this is the vertical component. I mean, this whole magnetic field exists in the magnetic meridian plane. Now, if you have a deep circle here in the magnetic meridian plane like this, you can have a magnet in a vertical plane which is fixed, and this one, this plane, at angle phi with magnetic meridian plane. So this will be the circle, and the magnet will make some angle, right? So here the angle made by the magnet with horizontal direction is delta dash. So here it makes delta, right? You know this delta, you know tan delta. What is tan delta? Tan delta is BV by BH. Now this delta dash is the dip in the vertical plane. I mean this vertical plane, it is also known as apparent dip, because the true angle of dip always happens to be in the magnetic meridian plane. This is apparent dip, delta dash. So let's see what is the meaning of this apparent dip. See here, this BH, the component of BH, the in this vertical plane is actually this BH cosine theta, and as you see, this component remains same for the vertical directions. It's all the same. So for this magnetic needle, south here and north here, it will point here. So this happens to be direction of the horizontal component, so BH cos theta, and this happens to be the vertical component, that's BV, and this is the resultant. So what is the dip delta dash? Apparent dip, tan delta dash is in this diagram, right? If you draw this diagram here, BH cos theta, BV, right, and this is delta dash. So what is tan delta dash? It is BV divided by BH cos theta. This is apparent dip at a place. Tan delta dash is BV by BH cos theta, or we can write tan delta dash is tan delta divided by sorry, it was cos phi rather, right? Cos phi. Just change it from theta to phi. Cos phi. Okay. So this tan delta dash equal to tan delta divided by cos phi. And also in the extreme case, say this is the magnetic meridian plane, this red one. Okay, now if you choose to keep the magnetic needle in another vertical plane which is perpendicular to the magnetic meridian plane. Then what will happen? See, this is 90 degree, right? This angle is 90 degree. This, remember, this is the horizontal. This is ground. If you keep a deep circle here the deep circle, you know it very well what is going to happen. Here this magnet, this deep is the true deep, and if there is a vertical plane containing a magnetic needle constrained to stay in the vertical plane, that's what deep circle is all about. There goes the circle, and here the magnet will point exactly vertically downwards. It is exactly vertically downwards. Why? Because here, see, 90 degree, right? So there you have these components, what, BH, and this component BV. In this plane, BH cos of 90, that's 0. So in this vertical plane, the horizontal component of Earth's magnetic field is 0. You have this vertical component only downwards, and that is why the magnet points downward. And also, you know, in the southern hemisphere, see, at the poles the magnet will behave like this, right? At the pole, this is at the north pole, and see, at the southern hemisphere, so in the region of southern hemisphere, the magnet will point like this, actually, north pole up and south pole down, because this is the direction of Earth's magnetic field. This we can understand very well, that the relation between deep and magnetic latitude lambda at a place. This will be quite clear from the diagram. Say this is the Earth, this is the north pole, of course magnetic, south pole, of course magnetic, this is the magnetic equator. So write equator bracket M for magnetic, and there is a point, this is the magnetic latitude lambda, and here, as I told you, that the model is like there is a magnetic needle having magnetic moment this way, south pole here and north pole here. So to find the magnetic field at this place, so here you can split it up into like this, right? If this is, so this is also delta, so this is M sine delta, this is M cosine delta. So due to M cosine delta, this is M, due to M cosine delta, this point is the broadside position. This is a point on the surface of the Earth. This point is the broadside position for this magnet M cos theta. So is it yeah, so what is the magnetic field here? This is mu 0 by 4 pi M cos lambda by r cube, where r is the radius of the Earth. Okay, now due to the same sine delta, this is the end side position, and this is mu 0 by 4 pi 2m sine delta divided by r cube. So as you see, this is the horizontal component of the Earth's magnetic field. This is horizontal and this is vertical. Vertical means towards the center of the Earth. Horizontal means tangent to the surface of the Earth. So BH I can write mu 0 by 4 pi m cos lambda by r cube, and BV is mu 0 by 4 pi 2m sin lambda by r cube. Therefore tan delta is equal to, divide it, tan delta, this is the angle of dip and this is the resultant magnetic field at that place. Tan delta is BV by BH, that is 2 tan lambda. So this is the expression you get, tan delta is equal to 2 tan lambda. Now from this expression you know it very well that at the southern hemisphere why the magnet will point upward, and why at the north pole magnet points downwards with north pole vertically downwards. Okay, that southern hemisphere one, I can show it with a diagram also. Magnetic equator, south pole, north pole, south pole magnetic. Take a point on the southern hemisphere. This is a magnetic needle, this point. So you split it up into two magnets. Yeah, that's it. So there lies the explanation that due to this, so it can be split up into two magnets here. Due to this magnet and this magnet, there will field. Due to this magnet, the field is vertically upward. So BV is vertically upward here, and BH is along horizontal. So at a certain place on Earth, if BV is upward and BH is like this, that means resultant field is in this direction, and that is why the north pole behaves in this way. There you have the north pole and there you have the south pole.